So today I'll be talking about some of the aspects that we have been looking into cancer biology and how the kinds of questions that we were looking there helped us dig deeper into what is going on in different COVID-19 patients. So once again, thank you to the coordinators. Thank you to all of you listening in on a Saturday morning. I'm sure you all have better things to do over the weekend, but thank you for tuning in. And thanks to all the members of the Cancer Systems Biology Laboratory, which I have the pleasure to lead. It's really their hard work and efforts that I get to be the mouthpiece on at such events. And on this auspicious event of Teachers' Day, let me once again wish a happy Teachers' Day to all the teachers who I've had outside the classroom or in the classroom, who have really taught me whatever so far and made me reach where I am today. And as I continue, happy Teachers' Day to all my colleagues, all my collaborators from whom we learn a lot while we tackle these difficult questions. And of course, last but not at all the least, to the members of the CSB lab, from whom again I learn a lot every single day, learning into about different new topics that they want to explore and so on. So of course, teachers and students cannot really exist without each other. There is a bidirectional interaction between them and also bidirectional learning, at least in my case, that happens. I learn a lot from all the students I interact with. And you'll hear a lot about all different feedback loops as we move along. Okay, so before we move into COVID, let me give you a brief glimpse of what the major work of our group focuses on. So most of our work focuses on trying to understand the process of metastasis, which is the process through which cancer cells spread from one organ to another. And how exactly this happens is through this fantastic set of freeways or highways in our body called blood vessels. So imagine there's a tumor in a given organ, and that particular those particular set of cells can get onto this freeway, travel to all different parts of the body, and then keep taking exits to form tumors there. And metastasis, so this spread, is what causes more than 90% of all cancer-related deaths, and it still remains an unsolved challenge in the clinic. So what we try to do is to develop mathematical models to understand this process better, and with the hope that if we have a deeper understanding of the dynamics of this process, we can try to stop metastasis and save all these different lives that are lost due to this process. Now, when I talk about mathematics and biology, these are not two terms which usually occur in the same sentence, because all of us are told that at the end of class 10th we have to choose either mathematics or biology. That's the usual career route, or at least it used to be when I was at that juncture in my life. So we end up choosing one or the other due to whatever different interests. But trust me, what is happening today is that these people who have bifurcated to do these different routes are coming together. And they're coming together because it's only by their coming together that the open questions that the bioengineering or biomedical engineering or different human diseases, such as COVID, for instance, that we face today, are going to be answered. So I am affiliated with this unit called Center for Biosystem Science and Engineering, especially to those outside IISc. This is a new department at IISc. I mean, new in the sense of at IISc time scale, it's new. And this department enables students as well as faculty members coming from engineering as well as biology disciplines to work together to try to answer some of the open questions in the field. Now, when I chose to go the engineering route in 2006 and started as an undergrad student at IIT Kanpur in biological sciences and bioengineering department, I had no clue how to merge these things together, or even if they can be merged in some possible way. So, I was very active in all different student activities at that point of time, really didn't know what to do in life in general, whether to do research or not. I was into theater, into student administration, etc. And one of the things which I was very keen on at that point of time was science journalism. And again, the COVID scenario helps put in perspective how important good science journalism is, good science communication is. So exactly 12 years ago, that is one more reason why this date is so special to me, we started the campus science magazine of IIT Kanpur called Nerd. which stands for Notes on Engineering Research and Development. And I was really at that point looking for a career in science journalism or science communication in general. And it is at this point that I was in Bangalore for a conference, and I happened to meet Professor Balaram, who was then the director of IISc. He was also then the editor of Current Science, if I remember correctly, and they used to have a fellowship in science writing. So I was talking to him. I had the fortune of speaking with him and telling him about what my interests were at that point of time and seeking his advice as to how to move forward. Because again, science writing or communication is not really a very straightforward field which has a very predefined trajectory. I mean, it's gotten better over past 10 years, but it's not. It was not there at least at that point of time. So he listened to me very patiently, and then he said that, is there nothing in science that interests you? And that really got me thinking that there are some questions that I want to answer, but I'm not sure if if I am in the I have the right set of tools or the right set of guidance to get there. Now, so at that point I was taking some courses in mathematical biology, biophysics that existed in physics and maths department at IIT Kanpur, and was getting decently interested in that. And this is where I came across another set of workshops led by this National Network for Mathematical and Computational Biology, which was being led by Professor Govindan Nangarajan, the current director of IISc, and Professor Somdatta Sinha. So, and I attended various of the workshops which are conducted by this unit, and it really helped me choose what exactly, helped me explore mathematical biology in general, what directions exist. So while I, didn't have the fortune to study at IISc, my career decisions were definitely shaped by the two directors of IISc and many other faculty members at IISc whose talks I attended as a part of this workshop and so on. So now, when exactly the sort of point of no return came that, yes, this is what I want to do for a good part of my life. So I was in my master's degree and working with Professor Pradeep Sinha, who is a developmental biologist, and trying to understand how cell patterning happens in a Drosophila wing. So I'd written down this set of equations, which, according to my naive understanding at that point of time, sort of represented different interactions that were going on among the different molecules in that setup. And the goal was, can we now try to explain what different kinds of patterns that are seen? So I presented this model to a set of biologists, and they just shot at me saying that, this is just a mathematical model. This has no connection whatsoever to reality. And I shot back at them and said, but what do you study? Well, whatever you study are also models. These are biological models instead of a mathematical model, right? So, I mean, no one really wants to cure cancer in mice. People want to cure cancer in humans, but they use mice as a model systems to study that how exactly cancer grows. And there are thousands of people out there who have cured cancer in mice, but have they been able to cure cancer in patients, right? So all different models, be it a mathematical or a biological, have their own strengths, limitations, and assumptions. And this, this particular one experience that I had sort of set me on that trajectory that, can we really try to integrate these two things, insights coming from maths and biology to gain a better understanding of the biological processes overall. So I applied for a PhD, got into Rice University. So I knew I wanted to do systems biology, but what exactly biological system is something which I was not very clear about. And then I came across this article, which was written by Professor Rachel Jacob, Professor Herbert Levine, who happened to be my PhD advisors later. They're both extremely well-renowned physicists, and they had been working on bacteria, trying to understand how bacteria communicate with one another. And they had written this article right around the time I joined Rice on how some of the lessons that they had learned in bacterial communication can be applied to think about cancer. And the middle author on this, Professor Coffey, is an extremely senior physician of prostate cancer. So it was refreshing to see how physicists and doctors can actually come together and start thinking about some topics together and so on. So that is what sort of set me on my path of trying to understand this process of metastasis. And metastasis, although I mentioned it causes more than 90% of deaths, but it's actually a highly inefficient process. More than 99.8% of cells which leave the primary tumor, which is where the cancer originates, are not able to form metastasis. And there are still no unique mutational signatures that have been identified. So we started thinking about this process as a dynamical process, something which physicists think about, for instance. So, when cells are moving, they are constantly changing how tightly they are talking to their neighbors, because the entire tumor cannot move. It's only a bunch of cells that, get segregated and move. Then, of course, they're changing their ability to migrate and invade. Now, there is immune system in the body, which I'll come to later, which is constantly attacking these cancer cells. So they have to find ways to evade those attacks, and they have to eventually reach a distant organ. Say for breast cancer cells, it can be lung or liver, and settle down there. And this organ has a completely different environment than their home organ. So how do they actually settle down and eventually form a whole new tumor there, which is what causes all these deaths of cancer patients? So we thought that to better restrict metastasis, and there's no therapy out there which restrict metastasis. All the therapies that you hear about, chemotherapy, radiation therapy, or even immunotherapy these days, is mostly restricted to bringing down the primary tumor size or number of cells. But once cells have spread, there is really no therapy that is out there. So we thought that maybe we need a better systems level understanding of this process to try to understand how to block this process. Now, of course, molecular biologists who have been looking into cancer over multiple years have done a fantastic job in identifying all the different molecules which are involved in cancer metastasis, for example. But if you have all the parts and they're not yet put together, does it really give rise to function? So if you have all these different car parts and you don't put them together, you cannot understand how a car moves. So function emerges when you put these things together. So this is what's called an emergent property, where whole is greater than sum of its parts. So we try to adopt a very similar approach when we look into metastasis, that if you have all these different molecules, do we know how they interact with one another? And then can we get a better understanding of how exactly the cancer cell moves, just as the car moves in this case. And what that process entails often is communication between developing mathematical models, which is what engineers, physicists, mathematicians typically do for any given process, and looking at the biological system simultaneously and see if there can be a crosstalk, if one of them can learn from the other, and vice versa. And at the end of the day, can we come up with a predictive understanding of whether cancer will metastasize or not, or how aggressively it will metastasize, and so on and so forth. Now, again, one idea is that people have been mapping out all these different molecules. They know which molecule interacts with what, and how does it change the different properties of a cell, be it cell proliferation, because cancer continues to divide much faster as compared to other normal cells in the body, or the ability to move, etc. So this is one picture where you can present cell as in some sort of an integrated circuit and see this is how things are interacting, and therefore you can get a better understanding of the process. But this is where I would like to highlight the difference in the understanding of the word understand itself. So to many biologists, if you know all different molecules and list them down, that is understanding. To various people trained in more quantitative aspects of things, unless you're able to predict accurately what is going on, you don't understand the system, right? So for instance, if I were to ask you to write a mathematical model for all these interactions, there is no time scale mentioned, there's no length scale mentioned, there's no information about whether each of these interactions is as strong as the other one, how direct, how non-direct, how non-linear, how combinatorial. If there are two links coming in the same node, then it's an AND gate or an OR gate or a multiplication, addition, etc., etc. None of that is mentioned here. And this is, what leads to unpleasant surprises in the clinic. So for instance, in the early 2000s, there was this idea that if you block angiogenesis, and angiogenesis means the growth of new blood vessels. So cancer cells are able to grow their own blood vessels. So if you block that, then you are depriving cancer cells of oxygen and nutrients, and therefore you should be able to take care of cancer. So clinical trials started. And what happened was that patients who received this therapy were giving worse outcomes as compared to patients who did not receive this therapy. So it was a complete opposite to what the expectation was. And it was only later people figured out why this was happening, because when you are basically cutting them, depriving them of oxygen and nutrients, you increase metastasis. So because now they are, searching for other avenues to go and do that. So again, cancer is not a static dumb system. It's an adaptive, evolving, dynamical system, and we need to appreciate that dynamics, that adaptive behavior that it has, because it's at the end of the day, it's our cells in the body. So again, and this is just not coming from me. This is the last sentence of the most cited review in the field of cancer biology, called Hallmarks of Cancer, where people identified this, some of the different features which are common across cancers, and said that one day we imagine that cancer biology and treatment will become a science and conceptual structure that and logical coherence that rivals that of chemistry or physics. Now, chemistry or physics, as you know, are disciplines of science where mathematical models and experimental observations go hand in hand. There is enough bidirectional communication that is going on. In biology, it's not as much, at least in cancer biology. 10 years later, when they wrote Hallmarks of Cancer, the second generation or the next generation, and added 4 other scenarios to it, and this is the second most cited review in the field of cancer biology. Again, they end by saying that we foresee cancer research will become a logical science which will have some underlying organizing principles. I'm waiting for the next article, hopefully in 2021 or 2022, and see what the opinion of these authors is. But again, as you can see, this is where the field sort of stands. We still don't understand the very basic laws or rules that these cancer cells tend to follow. So, how does a representative case look like? I'll just give you one example here. So, you put together some network, and these you read different papers, see what molecules interact with one another, and put together some network, and what activates. Activates means you increase the production rate, inhibits means you decrease the production rate. So you can represent them through a set of mathematical equations, ordinary or partial, depending on the questions of interest. So if you have once a set of coupled ordinary differential equations, then you can solve them and try to identify what the patterns is. But again, things should not end here. You should be able to make some predictions, because that's the power of mathematical modeling, and then go back in the lab and test those predictions. And once you test those predictions, new questions emerge. And this is what the feedback loop I was talking about. So you constantly need to change your model. You constantly need to adapt your model to incorporate whatever the latest information that we are learning about biology. Because again, biological systems are not designed by us per se, unlike an aeroplane or some air conditioner, where you already know that if this is broken, this is how to fix it. We still don't know all the connections that happen within these cells. So every time we do a new experiment, we figure out a new link, and then ideally that has to go back to your model, and then this cycle sort of has to continue in general. So what have we learned so far? I'll not go into the details. So I'm sure many of you have heard about this, that cancer, the way cancer progresses and the way an organism develops, there are many similarities. Yes, there are many similarities, but I would like to highlight one similarity which people don't really talk about too often. So again, this is some representation denoting how a pluripotent cell, which means a cell that has the ability to give rise to multiple different cell types in the body, because life starts with a single cell at the end of the day. So how does that give rise to all different kind of a cell? So you start with a single cell, but then when an organism is developed, you have lung cells, liver cells, heart cells, etc., etc. So how that process happens is what this landscape determines. So you have this this pluripotent cell at the top, and then these valleys represent all different cell types. So once a cell is in a valley, it stays there. So once a lung cell has been formed, it stays a lung cell. It doesn't randomly one day in the morning gets up and says, I want to be a heart cell, and so on, right? So there is that concept of stability which is built in here, and I'll get to that in a minute. But what you see here is that this particular cell, for instance, represented by blue, this can either become green or pink. Now, how does this individual cell decide whether to become green or pink? So we often hear that, oh, biology it's all in the DNA, everything is written, it's just a book, etc., etc. But here there's an element of chance. Here there is a coin toss that is happening, that this can either become this or become this. What determines that? There are various other factors which we are still exploring in general. But what I want to highlight is that it is not completely deterministic process. There is an element of chance, there is an element of uncertainty, there is an element of stochasticity which is built into this entire process. Okay, so that's a biology version of things. Now let's go to a physics version of things. So if you talk about some multi-stable system, there are 2 or more states in this top diagram. I hope you can see my pointer here. And so think of it. You design some some say plastic scenario like this. Put some little balls in that, and then just shuffle it or just perturb it. So what you will see is that some balls will switch from one value to the other value. Now this perturbation, in the context of biology, comes from noise which is present in the system. And the overall idea is that you have a stable state, or 2 stable states, and in between an unstable state, and cells can switch back and forth and so on. So does that mean that a lung cell can become a liver cell and a liver cell can become a lung cell? Yes, but the perturbation required is quite high, and that is not offered in our daily lives in general. But again, this is possible that they can switch. So nonetheless, what happens then as a consequence of that is that if we have a population of cells, some of which are say we are talking about drug resistance. So some cells are drug sensitive and some cells are drug resistant. So if you apply a drug sensitive cells should disappear and drug resistant cells should have no effect. But if cells can switch back and forth, then when you withdraw the drug, those drug resistant cells can give rise to drug sensitive cells and vice versa. So therefore, we need to think about this process more carefully. These are not static events. These are actually dynamical processes that are affecting things. So, when we talk of genetic processes, these are irreversible, deterministic, heritable. When we talk of such non-genetic processes, dynamical processes, phenotypical processes, then these are not necessarily always heritable. They are reversible, as I just mentioned, and there is an element of stochasticity that is involved. So basically what I'm trying to say is that cancer is not just genetic disease, it is much more than a geneticist Pandora's box. There are many, many more things that are going on than just alteration in the DNA sequence of a few genes, which are called oncogenes or tumor suppressor genes or whatever. So what we have learned so far is that this is literally a summary of 8 years of work by us and the entire community overall. And I'm summarizing here that if you look at the process of metastasis, there are various feedback loops that are multi-stable in nature, and because they are multi-stable, they allow switching back and forth in different states. So because cells have different states, they can change their behavior, they can change their adhesion, they can change their metabolism, they can change their drug resistance properties, etc., etc. And therefore they can adapt to the process of metastasis, because in the process of metastasis, the conditions around them are constantly changing, so they have to be able to adapt to that in general. And this is what is called non-genetic heterogeneity, which enables better fitness. And there was recent studies which have shown that if you break those feedback loops, you can actually reduce metastasis. So here we are coming up with a new mechanism saying that, what people thinking so far is that let's delete this molecule. They're saying, well, not necessarily. One other way is to interrupt with the network rather than, link rather than the node of a network. And of course, cancer is not happening at a cellular level. Cells are communicating with each other biochemically, biomechanically, etc., etc. And that communication itself is generating yet another set of properties, which is called an emergent property. So there is complexity within a cell, there is complexity in a tissue. So there is evolution that is happening at different length scales and time scales overall. Anyway, so when you start developing mathematical models, you need to know the biological question first, right? That is sort of a necessary condition. So let's say if you are asking questions, can cells coexist in more than one state? The similar kinds of questions I was talking about earlier. You can write down a set of, say, differential equations and do bifurcation analysis, space diagrams, etc. If you're asking a different set of questions, that now if you have this data that has been collected, can we classify which cell is in which state? Then you need some machine learning, statistical model kind of things. If you want to ask questions that this is all about a single cell, how are cells affecting each other? Then you get into partial differential equation kind of scenarios where because now you're looking at a tissue scale instead of a cell, and you can apply all different game theory and population dynamic kinds of models. So this is something I want to emphasize, that you need to know the biological question very, very, very precisely and clearly before starting to think about a mathematical model to represent that process. Because if you don't do that, then you're doomed for failure from the very beginning itself. Okay. And this is one of my favorite articles. It says, written by a mathematician who now works with biologists and does sort of systems biology, Jeremy Gunawardena at Harvard Medical School. And he says that There are certain rules which one needs to follow. One is to ask the question, which is what I was just saying. Building models for the sake of building models will keep mathematicians happy, but it will not really contribute anything to our understanding of biology. Okay, keep it simple. Again, you can include all the biochemical details, which will keep biologists happy, but that's a poor way to model. So you need to strike a balance somewhere. And you just don't need to think about fitting the model. You should be able to generate predictions which can be falsified eventually. It's a beautiful article if anyone of you is interested in reading it. All right, so that's all about cancer. I would like to thank the fantastic set of people that I have the fortune of working with, colleagues, collaborators, and again, they come from all different disciplines: cancer biology, clinicians, mathematicians, physicists, chemists, engineers, etc. Because again, cancer is such a complex process that one set of tools, one set of insights is not sufficient to understand it, and we really need to literally talk and integrate our findings across disciplines. So mathematical oncology is a growing field in general. There are various groups out there looking into this. These are the 10 hallmarks of cancer that I was mentioning about, and people have started modeling all of them. We look at invasion and metastasis, but there are other cases such as angiogenesis, which I was talking about, which also people have modeled and so on. And National Cancer Institute in the United States has started a whole new set of centers or projects called Physical Sciences with Oncology, where they get together physicists, engineers, together with cancer biologists and try to solve some of those open questions. This is the only math department I know of that exists in a cancer hospital. It's called Integrated Mathematical Oncology, and this is one of the top 10 cancer hospitals in the world. So if they are thinking about this, then hopefully there is some value. There's a group called Mathematical Oncology, if anyone of you is interested, which is a subgroup of Society for Mathematical Biology, which is a sort of a much larger cohort. And I've recently taken over as co-chair of this subgroup. So I'd be happy to answer any questions if anyone has about this particular subgroup of mathematical oncology. Anyway, coming to COVID. So, of course, this has devastated many lives in various different unimaginable forms and overall, and that, and for us, the more fortunate ones, Twitter sometimes provides these, little bursts of satire or laughter, or whatever, to look into the scenario that we are in. But again, when we are challenged with such major epidemic, then we again need expertise across disciplines. We cannot just rely on virologists or just on economists or engineers. We all need to come together and ask, try to help the way we can. And that is what has been going on. In this particular website lists out different efforts that have been going on at IISc to try to tackle the unusual, unprecedented scenario that we are in today. So, when we started thinking about COVID, the questions that we asked here were very much inspired from the questions that we try to answer in cancer progression. So when we saw the initial data in April, that patients were responding very differently, so we were asking, why is that happening? Just as why some patients show metastasis or more aggressive metastasis versus less aggressive metastasis. What host factors affect the severity of the disease? So is it really just host? Is it really just virus? Or is it really a combination of those which is giving rise to a set of properties? So again, in the context of metastasis, there is literature that say it's called organotropism, that not all cancers go to all different organs with equal probability. So some cancers, so prostate cancer has a probability or has a higher tendency to go to bone. Breast cancer has a higher tendency to grow to some other organ. So why does that happen? So there is some literature on that organ provides the right set of conditions for cells to grow. So similarly, what is the right set of conditions that the host provides for the virus to grow, and so on. So that is what we started looking into. Again, I don't really need to go into details about different symptoms that corona virus infected patients show and the different severity of it. There have been enough news reports about it, and more understanding that is coming along. And this seems to have the possibility of even long-term damage, even after the patient has recovered in all different ways. So it's really important that we understand what exactly is going on when, this particular virus infects a particular individual. And again, why are the responses different for older patients, for patients with diabetes, for patients with hypertension, etc. And again, a word of caution. I would request you all to also please stay safe and healthy, because yes, the likelihood of it getting worse in younger people is low, but that it's just a likelihood, it's a probability at the end of the day. Okay. So what factors determine the severity of the disease? So again, when we dug up the literature at that point, there was these host factors such as comorbidities, gender and age, ethnicity, and there were some viral factors, possibly viral load. So I'll just present some representative clinical data that we looked at that point of time. So this is the references for which are given here, and I'll be happy to talk more about it. But what you see here is that, so the y-axis is initial viral load in patients which showed a severe disease versus a mild disease. And this is the peak viral load, and this is again the initial viral load of patients with no comorbidities and one or more comorbidities. So again, what you see is that the viral load is not really different. So viral load can affect infectivity, but not necessarily the severity of a disease. So how much virus you get is not necessarily going to affect it, although again, these things may change because we are still learning a lot about this particular virus. And these are just some other results showing the same thing, that in mild versus severe, this is from a different cohort of patients. So some consistent literature that was coming around at that point of time. So the question we asked is, can the outcome depend on, if it's not depending on just the viral load, then can it depend on the interactions of virus and host and the properties that emerge with that? So what are the components of the model? This is the first question we have to ask. So, the most common cell, the most common organ that gets affected is lung. And the cells in the lung which get most affected are something called AT2 cells, or alveolar type 2 cells, which are usually involved in the gas exchange process of oxygen and carbon dioxide in the alveoli. So that's the host sort of part of things. Now, the other host part of things is the immune system. So there are, again, broadly speaking, innate immunity and adaptive immunity. Innate immunity is the set of mechanisms that kick in right as a foreign particle enters, and adaptive immunity is a set of mechanisms which kick in, with some delay after the first line of response has been activated. Innate immunity system. So innate immunity system again contains of many different types of immune cells. I'm just giving a very a bird's eye view here. So there are these cells called macrophages, which have the ability to what is called phagocytose, which means it sort of engulfs the foreign particle within itself and then shreds it into pieces and so on. That's the process that destructs the virus or bacteria or whatever foreign particle, depending on the size, of course. And then you have the response that comes much later, which is by T cells that you see in the adaptive immune system part. So these T cells are eventually can actually kill the virus in other ways as well. So they recognize the virus in different mechanisms that a macrophage does and so on. All right, now I must tell you that this is the first time we were dealing with immunology. I've not read immunology to that extent before. We know that there's an innate immunity, adaptive immune system, but not really much. And this beautiful article written by Ed Yong recently summarizes at least my feelings that immunology is where intuition goes to die. It is just so complicated that it's extremely hard to understand. And this is I'm sure many of you have read this joke, but this is how Ed Yong starts his article, to talk about this. So there's a joke about immunology. An immunologist and a cardiologist are kidnapped. The kidnaps threaten to shoot one of them, but promise to spare whoever has made the greater contribution to humanity. The cardiologist said, well, I've identified drugs that have saved the lives of millions of people. Impressed, the kidnappers turn to the immunologist and asks, what have you done? And the immunologist begins by saying, the thing is, the immune system is very complicated. And just afraid of that description itself, the cardiologist says, just shoot me now. Okay, so this is a joke, but again, every joke has an element of truth to it, as I'm sure you realize. The immune system is very complicated, and I was very nervous about how can we even begin to understand this. But again, being in a setup where you have experts around was extremely helpful. So I'm really grateful to my colleague Siddharth Jhunjhunwala, who's an immunoengineer, who really helped us understand to the degree that we needed it for the modeling perspective as to how these different immune cells are behaving. And I mean, the inhibition was lowered down a little bit because we have recently started working with him on some other aspects of immune system as well. So this was work led by Achyuta, which where we were trying to understand how immune cells make decisions. So just as I was talking about how cancer cells make decisions, we are now beginning to look at how immune cells make decisions. So we had some beginning into immunology, but still hats off to Siddharth who understands it, and he patiently really taught us what exactly might be going on in the context of COVID. Okay, disclaimers. All models are wrong, but some are useful. I'm sure you have seen many models, everyone trying to predict how exactly COVID will grow, when exactly the wave will come, etc., and you see different outcomes. What factors contribute to it? The factors of so-called human stochasticity. If people start doing parties, then how can you incorporate that into the model, for instance, right? So all models proceed on some assumptions, for instance. Another quote, the best model of a cat is another cat, and especially the same cat. Okay? A model is a lie that helps you see the truth. So any model that you see, any mathematical model or biological model, you should take it with as a pinch of salt. I mean, that's the whole critical thinking aspect of it. But this is one of my favorite by Albert Einstein, saying make everything as simple as possible, but not simpler. So when you're trying to represent such complex interactions through a set of mathematical equations, we need to be really sure about what is the level of granularity that you're going to talk about, what are the different assumptions, how do those different assumptions fail, and to what degree can you actually make predictions, and what are sort of more of a speculative scenarios in general. Okay. So we started to model the within host dynamics, which is sort of going on in viral cells in general. Looked into this again. We didn't really have to go too much further because there are experts around. Professor Narendra Dikshit, who has been looking into viral dynamics for a long period of time. So we looked into this, and we had actually done some modeling on how cancer and immune cells interact with each other earlier as well. So we came up with these molecules, these cells and how they are infecting each other. This work was led by Kishore and Sarthak. So infected cells, for instance, can produce virus that infect other cells, which is something we know. Infected cells can recruit macrophages and T cells. So each of them is represented by an arrow. So this is the proliferation part. Infected cells can recruit the macrophage and T cells. This is the red arrow. Then macrophage and CD8 cells can kill these cells. So that is this inhibitory red arrow. Then if there is too much antigen load, then CD8 cells can finally give up and say, well, I'm done. I cannot take care of more things. So that's the inhibitory arrow here. And then you have this regulatory setup in the cells, which can suppress the inflamed system. So these are some of the important components. So let's start with a simple case where we're only talking about the infected cells and macrophages, the first layer of defense. So you have infected cells, and you can write down a set of equations. What does this equation mean? Rate of change of infected cells as a function of time depends on some constant rate times the number of cells, because every cell is going to replicate eventually after the virus in that has done whatever it needs to do. And then there is a limit to which it can happen. So there is some this is called logistic growth in technical terms. So there is proliferation, and then there is some death term. So this is a production term minus the degradation term. So virus can be used up by the macrophage, and therefore you can have a less effect of the virus or number of infected cells eventually. Then you have the innate immune system. So how do their rates change as a function of time? There is a recruitment that is happening. So when there is virus, so that's why you have V in the numerator, and there's a saturating function here. Then innate cells themselves can recruit more. So this is this black arrow. That is why you have, and this is a nonlinear function. So you have m to the power n in the numerator and denominator. Now, one other thing which innate immune system cells do is that if there is no virus, they shut themselves off. Because again, the immune system response has to be balanced. If there is no foreign infection, then these cells should wait for some time, and then you're like, okay, fine, we are done. Our job is done. Let's go home. So there's that self-suppression, and then there is some clearance state, because not everything is immortal. So the cells die at some rate. Then we came up with another variable, which is called immunopathology, which measures the degree of lung damage. So this lung damage can happen from innate immune cells, from viral infected cells. Both of them can affect, and then of course there's some natural recovery that is happening. So again, this is here. Okay, so what happens as a function of these interactions? So here what you see is that we are plotting innate immune cells as a function of time for some parameter region. So what you can see importantly is that innate immune systems number of cells can also continue to vary as a function of time. So it's not just a monotonic response. There is interesting dynamics that is going on here. But nonetheless, the key messages here are, so if you vary the killing strength of the innate immune system on one hand and the self-suppression of an innate immune system on the other hand. So what are the different outcomes that you can see? So you can see an outcome. This is what is plotted here is number of infected cells. So if innate system is weak, what you see is that the disease can progress. Not surprising. If the innate system is strong and the self-suppression is weak, then the disease can regress. But there can be a region in which the disease can progress for slightly longer periods of time. So those are the different options. Okay? Now let's see immunopathology part. So there is a reason, again, these are the same two parameters here. There is a region in which the immunopathology is minimal. Now let's build in the adaptive immune system part. So this is the adaptive equation for adaptive immune system, the CD8 plus T cells. Now what happens is that, as I was mentioning earlier, this system kicks in a little bit later. So that's why you have this delay term in the differential equation. The other terms are largely similar. So again, viral cells can affect the stimulation of adaptive cells, and eventually adaptive cells can just give up. So that is this particular term, which depends on both C. It depends on C here, and then there is a usual clearance rate that goes on. Okay, so what happens if you include adaptive? So let's take a scenario in which without adaptive, which is shown by dotted lines, the number of infected cells on the y-axis and number of the x-axis is time. So what you are seeing is that without the adaptive, these cells were quite high, and they continue to be quite high for a very long period of time. But when you include adaptive, the virus response shuts down. And similarly, immunopathology also decreases. So adaptive immune system is able to help the innate immune system when the innate immune system itself is not able to take care of things. Okay. Now again, you draw these diagrams. X-axis is the killing strength of adaptive immune. Y-axis is the killing strength of innate immune. So what we see here is, again, the color still represents the number of cells. So if any one of them is strong enough, it's fine. But only when both of them are weak, then we have a much higher probability of getting into these kinds of issues. Okay? Then we further studied, let's say that only the innate immune system is strong or only the adaptive immune system is strong. And both of them, what we see is that the infected cells, are controlled within 10 days in general, and the immunopathology is also sort of lower. So, and then we varied these parameters and found that this time can change to 15 days and so on. But that's the idea, that as long as one arm is sufficiently strong enough, you can see clearance, and this is what we would call as the asymptomatic or mild cases, that the immune system is taking care of things right away. This is again just some data collected from different patients, where again you see within 15 days, generally speaking, the viral load has come down and the severity of the disease has usually come down. Now, what happens in the context of severe phenotypes? So I'll walk you through each one of them one by one. So these are the same plots. Blue is infected cells. Solid orange line is innate immune system, and the dotted line is adaptive immune system. X-axis is time, and the lower panel is all about immunopathology. Okay. So let's say if the innate immune system has the self-suppression that it has is weaker. So what will happen in that case is that the innate immune system will not go to zero, as in the response will not resolve itself completely. It will stay, and because it will stay, it will continue to cause some damage to the system. So while the virus has disappeared, there is still some lung damage that is going to happen. Okay. Then in other case, let's see what happens if you have a weak adaptive immune system. So if you have a weak adaptive immune system, so the innate is fine, it's doing its job. But again, the adaptive immune system is not really able to take care of things. You get virus resolution, but it happens much later. And by then, the immunopathology has also gone up, generally speaking. So you can still, these are probably patients who would end up in ICU at some point when both of them are weak. then you see viral load just continues forever, immunopathology just continues forever, and these are scenarios which are probably which might lead to fatality and with a high viral load at birth. Okay? So weaker adaptive immune system is generally the case with older people, and there is literature which I'll come to which has shown that the older people, this is weak. These are cases when both arms of the immune system is weak. So that is the immunocompromised patient with different diseases that affect their immune system overall. And this is a case where everything looks okay, generally speaking. The virus is also getting resolved in 10 days or so. But in some cases, because the lung damage has happened, because again, the major reason COVID causes is the lung damage or the tissue damage. The tissue damage is persistent. So this is a possibility where the younger people who still have a perfectly functioning immune system, except the weak resolution of itself, can give rise to that. Okay? Now let's talk about the third component, the T regulatory cells. So again, you write down a set of equations. There is again a delay because regulatory cells come in slightly later. The function of regulatory cells is that to tell the innate and immune system that yes, your job is done, you can go home now. So again, these are recruited by the viral cells, again through some indirect mechanisms which I'll not go into detail, and then there is of course some clearance that is going on. So what happens in this case? So let's say if you don't have any regulatory setup. So if you don't have any regulatory setup, what you see is that virus is still getting cleared in this particular parameter region, but without regulatory, you see immunopathology is increasing, but when you incorporate the effect of these regulatory T cells, immunopathology goes down. Okay. So one role of T regulatory cells is to sort of reduce the damage even when the virus has disappeared in some way. So sort of clear up the mess that the virus has created. But it is very important that these cells come in at the right time. So let's say if they come in this scenario, where it takes 20 days, this is the other case that I was talking about earlier, for the virus to clear down, and regulatory cells come in earlier. So if they come in earlier, then they are suppressing the innate and adaptive immune system, and finally the virus wins, or the infected cells win. So again, their timing is very important, and their dose is very important. But even if they come at the right time, if they suppress immune system too much, again, you have made a case where the virus has an advantage. So, balance in both the dose and time of arrival of these T regulatory cells is crucial, generally speaking. Now, how do we explain comorbidity? As I mentioned, in older patients, the CD8 plus T cells response is weaker, generally speaking. And in diabetes scenarios where you have elevated glucose levels, this favors the infection of coronavirus, generally speaking. Now, one other thing, sort of the last things to touch base upon is that just reducing viral dose may not be sufficient, because reducing viral dose is not always going to change the tissue damage that has already been caused. So therefore, one needs to consider some sort of immunomodulatory responses also. So these are just some scenarios showing that when you do some intervention, and here intervention is basically reducing the viral infection rate. So these are whatever some of your antiviral drugs will do. So you see that the clearance happens a little bit faster and so on. But what you don't necessarily see all the time is that immunopathology goes down. So you see that infection clearance time is getting better. The higher the efficacy of bringing down the replication rate or the proliferation rate of virus, the faster the virus will get cleared. But it might leave marks of lung damage in general. So just something to bear in mind. So I'll just conclude here that we set up a very, very minimal model where the question was that how is this interplay between host and virus affecting things, and we tried to look into what are the different dynamics possible and how can we map them onto the different clinical phenotypes that are there. And what we are able to see is that it's really the delicate balance that exists both in dose and in time of the viral cells, of the innate immune system, of the adaptive immune system that is really causing these scenarios in general. All right, so I'll end with a couple of just quick take-home messages. Then there's some other work that we are doing on coronavirus. So we are again working across disciplines. We are working with Professor Nandi, who's a very well-known immunologist, looking into how the flu vaccination or BCG vaccination can correlate with COVID deaths. Then we're also working with Professor Datta at IIT Ropar who is a mathematician and trying to understand, can we predict the incidence curve of a country of coronavirus? And these are all up there on Research Square, and this is published. So I'll be happy to answer any questions. And with the developmental biology group at NIRH, Mumbai, this is something that we recently published and got quite a bit of media attention, where we showed that it is possible that the placenta can be infected by COVID. So, I'm not saying this can be vertically transmitted necessarily, but placenta can also be affected. So there is some risk there also involved. All right. So just these quick take-home messages. Always hear about what, how do you get to answers? How do you, find the answer to a question? Please, research. When you are in research, when you're in academia, it is not about the right set of answers. It is about the right set of questions. Because, if you get interested in some process, just start studying it from whatever you know at that point of time. Okay? Because, at the end of the day, everything is connected. So today, and this is a famous cartoon of the elephant and blind men. Today, you might say, oh, whatever process you're looking at is a snake. But then when you gain a different perspective, you'll say, no, it's a tree, and so on and so forth, right? So, but what you see is that this is one integrated object. So, answers really don't matter, questions matter, and there are no stupid questions, there are only stupid answers. So I would request you all to always bear that in mind. Whatever interests you, pursue that, read about that, try that out. What is the worst thing? You'll fail. Okay, fine. Failure is the stepping stone that will keep you further. And again, the other thing I hear people talking about, or students saying that, well, how do you identify the questions? And or people giving this advice that you should identify a passion and pursue it. I have a slightly different take on it. I'm like, sure, that's fine, but pursue what interests you today. And eventually you'll find whatever interests you the most, and that you will, provided other boundary conditions in life, you will be able to pursue that in general. Okay, so let me give you an example. So I was born and brought up in UP, Uttar Pradesh. Okay, and there is, and again, every joke has an element of truth to it. Okay, so if you are born in UP and Bihar, or some radius close by, and you do not appear for UPSC, then you will be reborn in UP and Bihar forever, unless you appear for that. And just filling the form doesn't matter. You have to actually prepare for it and appear for it, right? So this was the scenario that was around me, and I was constantly interested in science journalism. And it was this fortuitous meeting with Professor Balaram which sort of set me into this direction that no, there are enough questions that I want to answer. And this is one of my favorite quotes by Professor Richard Feynman, saying that fall in love with some activity and do it. Nobody ever figures out what life is all about, and it doesn't matter. And then there's a whole details to it. But yeah, don't keep pursuing. Oh, one day you're going to sit under a tree and some inspiration will come. You pursue whatever your interests you today, and things connect. If you can look at cancer and then apply similar things to look at COVID, you can really move ahead and do other things. And finally, participate in learning from people around you, asking questions which are similar or different. Because trust me, it's not the journey that matters. It's not the destination that matters. What matters most is the company. So if you have surrounded yourself with curious people who you have to learn from, and try to learn from everybody as much as you can, then you will have a really enjoyable whatever pursuit that you are in. With that, I would like to thank you once again, and I'll be happy to take any questions.
Thank you so much, Professor Jolly. I'll start out with the questions. So, one of the first question received is, which subfields of math are heavily involved in biomathematics and biomodeling?
So mostly what I've seen is that the applied mathematics field, which looks into sort of nonlinear dynamics kind of scenarios, is something that is very active. But there are other fields also looking at topology and other scenarios where people have so depending on the question of interest, different fields can be applied.
Okay. Why did you choose bioengineering as your stream in IIT Kanpur? Any particular reason?
So it's always a mix of reasons in your control and outside your control. The outside reason being a JE rank, and the in reason being okay when whatever finds you interesting at that point of time.
What unique challenges do you face while conducting interdisciplinary research involving biology, math, and computer science?
So the most challenging thing is to parse through different languages, I would say, and realize that that language is a barrier. So if you're using say the word differentiation means something completely different to a mathematician versus to a biologist. So once people start to realize that, there are ways to connect, but it is this language, the barriers that we have built around ourselves, which are extremely helpful for, when you are in that room where everyone understands the same language. But realizing this and then moving forward is something which is the biggest challenge that at least I have seen so far.
In case you use machine learning in your research, what percentage of your algorithms are coded from scratch and what percentage is used directly from library functions?
Right. So this questions for which I mentioned, we are using machine learning kind of models. The kind of data that allows us to operate that is very recent. So this is a new development that we have only recently started looking into. So far we are looking into logistic regression models, but we have also come across other support vector machines and kinds of models which people build. And if there is a need that we need to write our own algorithm to answer a specific question, given there is data, we'll be happy to do it.
Is there a connection between cancer and COVID? Also, do you think that there is a metastasis-like transition that could be brought about by viral genes?
It's an excellent question. I have not seen so far any literature on that, but that doesn't mean that it cannot happen. There are some reports on cancer patients being more susceptible to COVID, although why that would happen is something which is possibly unclear at the moment. One of the reasons can be the involvement, involvement of immune system. It's already busy taking care of other things, so it might be slightly less involved. But there can be other reasons which I'm not aware of.
Sir, as you mentioned regarding the transformation barrier in developmental process is significantly high, is it possible to artificially provide that energy? In that case, can we actually transform the lung cell into a liver cell?
Right. So again, an excellent question. I think there's this whole field of what is called cellular reprogramming, where people are trying to see if one kind of cell can be pushed to become the other kind of cell. This I think got the Nobel Prize in 2016, if I'm not wrong, one of the fastest Nobel Prizes that have been given since the discovery. But what you see is that even in that case, the efficiency of reprogramming is extremely low. It's much less than 1%. So which means that these cells have some very tight barriers around them, which are there for a reason, because you want them to be stable. But how can you, first of all, what those barriers are, at what different levels they exist in biology in terms of regulation, transcription, translation, epigenetic, etc., and how can we break them specifically enough that it goes to a liver and not some other random cell type, is something which we are still figuring out. We have only scratched the surface of that.
What exactly is meant by expression noise and how is it modeled?
Right. So expression noise basically means that every cell will have a slightly different rate of production of mRNA. So from DNA you convert to mRNA, a process called transcription, and then mRNA converts to protein, a process called translation, which is what forms the central dogma of biology, molecular biology. So at the end of the day, these are all chemical processes which are dependent on the fact that the RNA providing machinery, the transcription machinery, has to come and interact with the DNA. Now, is it interacting with that particular element of the DNA which is producing that particular gene at all time points? Is not happening, because there's a lot of binding and unbinding that is constantly going on, which alters that in a given instant, the rate of production of this gene is likely to be very different than what it's going to be in next time point. Or if you're talking about a population, then in that population, the rate of transcription of different cells can be very varying. So that is what is expression noise. People model it using all different kinds of stochastic formalisms, and I'll be happy to chat more about them.
In your opinion, which model is better? A mathematical model proposed by a scientist or a model trained using machine learning?
So all models are wrong, but some are useful. I would not say there's one that is better because better or worse always depends in the context of the question. So if machine learning is helping us doing it, sure, okay. It's like a black box where mechanism is relatively opaque. And I happen to be a big fan of mechanism-based models, but that will not color my opinion in general. If it is answering that particular question and has the predictive power, sure, that's fine.
How do you quantify things like cell suppression of innate immune cells and the different types of lung damage?
Right. So again, the parameters that we have in the model, the self-suppression. So this is the parameters quantified for that are based on experimental literature in terms of when exactly this so-called activity of innate immune system began to disappear. So this can be from experiments coming in vitro settings where these cells are put together and then see how that is happening. Lung damage, that immunopathology, how exactly we map it to the degree of lung damage, we have not yet done it. We have treated it at a very, very qualitative level so far. One way is to have a tissue level model for this multi-scale model where there are different cells interacting with one another and they are changing the proliferation rate and you can actually see the damage that is happening. Our model is not at that resolution at this stage.
In the severe phenotypes graph, shouldn't the area under the curve correspond to net damage done? In that case, having a weak suppression, top left graph, should be better than the other options, right?
So again, the way we have defined immunopathology, we're saying that the instantaneous level of that is what is going to cause damage at that time point. So, but yes, area under the curve can be another feature which can be looked at. And as I said, again, whether the integral or the instantaneous value matters more is something we have not done. We have only described it at a qualitative level so far. But I'll be happy to see if there is any data that we can map it to and then see which of them is a better readout of the damage.
Can you please explain the cause of clearance terms in the model?
So the clearance term is sort of some self-decay. Not every cell will live forever. Every cell dies. It has a half-life, and that half-life is usually available from experimental literature. And it typically follows a first-order kinetics. So dx dt equals to minus k times x. So if you have the half-life available, you can figure out that degradation term.
The last question, one audience member has asked, what books do you recommend I read to get started with math bio as a math major?
So as a math major, one of the good set of books is by J.D. Murray, Professor J.D. Murray, called Mathematical Biology Part 1 and Part 2. There's another book called A First Course in Mathematical Biology, if I remember the name of the book correctly. It's by Professor Leah Keshet at University of British Columbia.